and for giving me the opportunity to give this talk. I would like to talk about the Brunn-Minkowski inequality and the Borell-Brascamp-Lieb inequality. The Brunn-Minkowski inequality is a fundamental inequality in geometric analysis, and it is essential because it yields many inequalities used in various fields. For example, the Brunn-Minkowski inequality implies the isomerimetric inequality. It states that among all sets with the fixed volume, the surface area is minimized when the set is a ball. This explains why the soap bubble are spherical. Then we will not discuss the further application about the Brunn-Minkowski inequality, but we will focus on the related inequality known as the Borell-Brascamp-Lieb inequality. And this inequality is a kind of the functional extension of the Brunn-Minkowski inequality. The Borell-Brascamp-Lieb inequality can be proved by induction on the dimension without using the Brunn-Minkowski inequality. By contrast, it seems difficult to prove the Brunn-Minkowski inequality by induction on the dimension without using the statements essentially equivalent to the Borell-Brascamp-Lieb inequality. It seems very interesting to me. So in this talk, we will focus on these things briefly. First, we see the setting of the Brunn-Minkowski inequality. And for two sets A and B, the Minkowski sum of A plus B is defined as the set of A plus B, where A belongs to A and B belongs to B. Here is the two-dimensional illustrations of the Minkowski sum. If A belongs to A and B belongs to B, then the sum of A and B is given by the diagonal of this parallelogram. Then this point belongs to the Minkowski sum A plus B. Then we write mu A by the volume of A. Precisely, it is called the Lebesgue measure of A. In the two-dimensional case, mu A is the area of A. Then we consider the next question. What is the minimum of mu A plus B when mu A and mu B are fixed? The shapes of A and B may vary, but the volumes of them remains fixed. Then how small can the Minkowski sum be? To investigate this question, we'll consider the next example. For positive value L and M, let A equal CL and B equal CM, where CL is defined as a set of vectors whose components is between 0 and L. It is called the hypercube. Here is a two-dimensional illustration. In this case, A and B are squares, and the Minkowski sum is also a square whose side length is equal to L plus M. Then A plus B is equal to CL plus M. In this case, the volume of A is the volume of CL, so it is equal to L to the power M. Similarly, mu B is equal to M to the power M. Moreover, the volume of the Minkowski sum is equal to L plus M to the power M. And then, we obtain the following inequality. The volume of Minkowski sum to the power n inverse is equal to L plus M. So it is the volume of A to the power n inverse plus the volume of B to the power n inverse. In fact, this is the case when the Minkowski sum, the volume of the Minkowski sum is the smallest. It can be expressed by the next inequality known as the Brunn-Minkowski inequality. The mu A plus B to the power n inverse is not less than mu A to the power n inverse plus mu B to the power n inverse. In addition to this example, there are other cases that this equality holds. The equality condition is that A and B are convex sets and they are homothetic. That is similar without rotation. And then, for example, if A and B are both, and then the equality of the Brunn-Minkowski inequality holds. This theorem answers the question 1. Indeed, the minimum of mu A plus B is given by this value. And next, we consider the following question. How can the Brunn-Minkowski inequality be proved? There are many known proof of the Brunn-Minkowski inequality. In this talk, we discuss the proof based on the Borell-Brascamp-Lieb inequality. This is a statement. If the positive functions f, g, and h on Rn satisfy this inequality for any xy with these inequalities, then the integral of h is not more less than the minimum of the integral of f and g. This inequality is somewhat, and this statement is somewhat complicated, but an important point is that the Borell-Brascamp-Lieb inequality is a kind of the generalization of the Brunn-Minkowski inequality. Indeed, the Brunn-Minkowski inequality is obtained by applying the Borell-Brascamp-Lieb inequality to suitable multiples of the indicator functions, where the indicator function of A is defined to be 1 if x in A and 0 if x not in A. We consider how can the Borell-Brascamp-Lieb inequality be proved. In fact, this inequality can be proved by the mathematical induction on the dimension n. For example, in two-dimensional case, we integrate the original function in the in y direction at first, and we apply the one-dimensional Borell-Brascamp-Lieb inequality. Then we integrate the resulting function in x direction, and we again apply the one-dimensional Borell-Brascamp-Lieb inequality. In this way, we can obtain the two-dimensional Borell-Brascamp-Lieb inequality. By contrast, it seems difficult to prove theorem 3 by induction on the dimension without using statements essentially equivalent to the Borell-Brascamp-Lieb inequality. For example, in two-dimensional case, to calculate the area of A, we integrate the indicator function in y direction, and we integrate the results function in x direction. Then the one-dimensional Brunn-Minkowski inequality is valid only for the indicator function on R. So the more general inequality applicable to the any functions is required. So that is why the Borell-Brascamp-Lieb inequality plays an important role on that's why the Borell-Brascamp-Lieb inequality plays an important role in proving the Borell-Brascamp-Lieb inequality by induction on the dimension. Okay, that's all. Thank you.
Thank you very much, Satomi-san. First, any questions from the non-specialist? Yes.
I am a physicist, so no expert. So this is a pure mathematics problem.
Yes.
I don't know whether there's any application to physics.
Yeah. I am not familiar with the application in physics, but in the paper of the Brascamp and Lieb, it can be applicable to the diffusion equation. So in this paper, to investigate the convexity of the potential, we can obtain the shapes of we can investigate the shapes of the ground shapes of the wave function. So the Borell-Brascamp-Lieb inequality can be applicable in physics.
Thank you.
I just said a little more detail. So this Brascamp-Lieb paper is a very famous one. Generally, this is very useful because it shows that log concavity is preserved by diffusion, and this resulted in the first rigorous proof of crystallization in 1D plus that I know of. So is it the Jennings model where you get the Wigner lattice out? It's they used it at the ground state of the Jennings model. This Wigner lattice is strong.
So this loop is area of the loop?
Yeah.
Any other? Yes, please. Very light question. So convenient explanation is sounded almost like the Borell-Brascamp-Lieb inequality is broader in the sense that it can prove the Brunn-Minkowski inequality almost immediately. But it's in mathematics, is it is Brunn-Minkowski inequality more important, or
Sorry, one more thing.
okay? Here they use the Borell-Brascamp-Lieb inequality
Yeah.
to prove Brunn-Minkowski inequality. So it almost sounded like the Borell-Brascamp-Lieb inequality has broader applications in mathematics. But is it true, or is Brunn-Minkowski inequality considered more important result in mathematics?
Yes, yes. Both of the Brunn-Minkowski inequality and the Borell-Brascamp-Lieb inequality are very important, but in pure mathematics, the Brunn-Minkowski inequality is the Borell-Brascamp-Lieb inequality is a generalization of the Brunn-Minkowski inequality. So the Brunn-Minkowski the application of the Brunn-Minkowski inequality can be regarded as the Borell-Brascamp the application of the Borell-Brascamp-Lieb inequality. So moreover, the application of the Borell-Brascamp-Lieb inequality is more wide. For example, the Borell-Brascamp-Lieb inequality can be applied for the partial differential equation and so on. So they are very important.
May I ask a question? So, what do you mean by saying seems difficult? It doesn't mean impossible.
I think it is impossible, but it is not sure. So I write that it seems difficult.
So how do you know it is impossible?
So it is not. So the considering by the induction on the dimension. So it is natural to the it is natural to consider the inequality on the all shapes of functions. So it is natural to consider the Borell-Brascamp-Lieb inequality. So so so
If I'm asking that enough for creation, I'm free answer. So yes, please.
So can one generalize this inequality to say Riemann manifold or some other stuff, or
yes, yes, it is a nice question. And at first, the generalization of the Brunn-Minkowski inequality is known. In the setting of the Lie groups. So in this case, the Lie groups, the volume of the on the Lie groups is for the whole measure, and Lie groups has the summation as a product. So we can consider the Brunn-Minkowski inequality of Lie group version. So in this case, the similar inequality is true in
so
the
even non-compatible?
yes, yes. So the Brunn-Minkowski inequality on the Lie groups are known. On the other hand, the legal version of the Borell-Brascamp-Lieb inequality is not known as far as I know.
Yes.
So I'm curious about whether we can sharpen the estimate the theorem 5 where you have the inequality between theorems. And so my first question is, what is the non-trivial condition when you have the equality? And second is, when can we have tighter estimate for this?
There is a case when the equality holds, but the equality condition is very difficult. So the equality condition is so complicated to explain, but the one is that these two integrals are same, and that this equality holds, and so yes, and so the shapes of f and g is same up to scalar on vertical and horizontal, and f and g is p. Sorry, f and g are these functions. These functions are the convex functions. All of them is true simultaneously. If the all of true simultaneously, the equality of Borell-Brascamp-Lieb inequality is 4.
Then that sounds like it's very difficult to have sharper lower bound.
Yeah. So it is so difficult.
Yes.
If we take n the dimension n to infinity, inequality seems to be reduced to just the inequality between logarithms, right? I mean,
I don't know.
the Brunn-Minkowski inequality, each term has power 1 over n. So if n is very large, it becomes log. Is it correct?
Oh, yes.
So it gets easier when n is larger, not large, but
Issue with the definition in infinite dimensions.
so
We don't have an infinite dimensional dimension.
what happens in that case? Is it trivial? The inequality.
I don't know about Brunn-Minkowski. Borell-Brascamp-Lieb does generalize the absolute. Infinite.
Antoine.
So I have the same question, but I think the answer. Is there something special about the Lebesgue measure? Because you mentioned the Hall measure on D groups, so I guess you need some translation invariance or something for.
Yes.
He said yes.
Yeah, so it proves you do. So there is a Riemannian version for Brunn-Minkowski. I'll shut up.
So yeah, open to mathematicians. Yeah. Yes, please. Yeah.
Wait, you were still asking the question.
Yeah.
So is it true for you another measure than the Lebesgue measure?
One more thing, please.
Another measure than the Lebesgue measure?
Yes. Sorry, do you ask?
Take a Gaussian measure instead of the Lebesgue measure. I mean, just because here the volume is the Lebesgue measure.
Yes, yes.
But if you take another measure.
Do you ask in the other major version?
Yes.
Yeah. So I don't know, but in the Lee group version, all the groups has the generalization of the Rubik measure. It is invariant measure in the action of the elements. So in this case, it is known in the of the Brunn-Minkowski inequality. But the other case, in other case, I don't know.
This triple trio, like.
You finished? Yeah, please.
I wanted to ask a little bit strange question. So in some parts of mathematics, you have this matrix which satisfies stronger triangle identity, called ultra matrix. This condition written there looks exactly like the dual of that condition. I'm not sure what to make out of it, but I was wondering if there is some kind of theory behind this type of inequalities. As you can think that you have this space of functions, then you have this operation, kind of convolution-like operation, and then you have this type of and then the integration of this function gives you some kind of norm, and then you have some kind of inequality of this sort, which looks kind of like the dual of what you think is an ultra measure. So I was wondering if anything like this is known.
So
I mean, sorry, it's just random. Similar. I also had a different question. So you mentioned you kind of motivate your dog to say that you have these two inequalities. One is kind of like very naive, you just work with measures of sets, and then you have this inequality. Another one is maybe more complicated, but to me as a mathematician, it looks way more natural because again, it's some inequality which lives in the world of function spaces.
Yeah.
Unlike that one. So why would you want a proof which does not use that theorem?
So so one reason of the importance of the Brunn-Minkowski inequality is that there are many proof of this, and these proofs are respectively important. So and this by the proof by using the Borell-Brascamp-Lieb inequality is also important, but the other proof of the Brunn-Minkowski inequality can be applicable to other other mathematical things. So the importance of the Brunn-Minkowski inequality is also the important. So
I see. So there are other proofs which do not look like this at all, and yet they still use this Borell-Brascamp-Lieb inequality implicitly in some different form.
yeah.
Thank you.
Any other questions? Finally, may I ask how these inequalities are related to your study?
I am studying about the many inequalities on the Lie group or the locally compact groups, and so that especially I am studying about the Young's composition inequality, and it is the Brunn-Minkowski inequality can be proved by using the Young's convolution inequality. So I am interested in the Brunn-Minkowski inequality, and the another is the generalization of the Borell-Brascamp-Lieb inequality of the Lie groups. So as I said, the Lie group version of the Brunn-Minkowski inequality are known, but is known, but the Lie group version of the Borell-Brascamp-Lieb inequality are not known. So I am interested in the whether such a generalization exists.
Thank you. I think the biologists like me somehow follow that topic. And thank you very much.